Hello, this is my submission for Project 2, Part 1, the airfoil simulated over a motor frequency of 60 Hertz. So as you can see right here, I have the geometry. So let's just go right. Once you get that loaded up, you're going to go over here. So I have another video explaining how to import this geometry, and the first video that I put out speaks about how I created the actual wind tunnel shape itself. But to briefly recap, you import these points, turn those points into a line, turn those edges into a surface, and then with this surface and this surface, you subtract them using a Boolean operator. And that's how, if you watch the other video, it goes into greater depth about how to get this shape. But for the purposes of this video, that will be all. Now you're going to go into the meshing software. All right, once you have the meshing software, it should look something like this. Let me go through what I did. So I was having issues with convergence in the next step, and that was mainly due to when you're using the triangle method, this edge right here would create an over-skewed geometry. So I went ahead and I just used the quadrilateral dominant method, and I decreased my meshing size. So if we go into sizing, default element size is 0.002, and that produced a pretty fine mesh. But more importantly, it allowed me to, if we go into skewness graph, it kept my maximum skewing relatively low. I still have some elements that approach closer to 1, but it's low enough for the purposes of what we're doing right now. And more importantly, it allowed me to converge in my actual software. Here we are inside of the solver, so I'll just quickly go through my settings. I have the energy equation on, and I have the viscous model on, K epsilon standard, and I only use the standard wall function where previously I've used enhanced wall treatment. This is because I was having issues with convergence, but this seemed to fix it. Okay. As you can see, I have my airfoil and my wall in a wall boundary condition. For the inlet velocity, my group found that at the inlet for 60 Hertz motor frequency, it was 12.5 meters per second. Importantly, to get the drag and force coefficients, what you do is you go onto report definitions, new, force report, drag, and then right here you would just say drag, just whatever you want to name it, click drag coefficient, and then what boundary condition you want to calculate that over. I already have it, but that's how you would do it. Now, for initialization, just a standard hybrid initialization. I've already done it, but I'll do it again. All right, so now that the initialization is done, we're going to go ahead and run the calculation. I put on 250 iterations. All right, so the calculation has completed and it converged in 37 solutions. It's pretty good. You can see our drag coefficient and our force coefficient, drag force coefficient, have did converge as well. So now if we go under something like contour, and let's go ahead and do the velocity contour, compute that, save and display. Yeah, and this is to be expected, right? You see there's a small wake region, even though this body is a relatively streamlined body. There is a small wake region, and it does have an effect throughout the rest of the body. And then you can also find under report definitions, force drag coefficient, compute that, and it pops up down here. This would be our drag coefficient. This has wrapped up the simulation for the 60 hertz motor frequency airfoil. By the way, it's a NACA 4412 airfoil that wraps up the simulation for this part of the project. Thank you.